Hi, this is Mr. Merrill, and in this video I'm going to walk through 6 commonly missed problems on the practice test, and you can skip ahead if you want to see exactly which those problems are. Otherwise, we're going to get started here with the first one, and there's definitely going to be a question like this on the test. It's a position versus time graph, and it's asking for the instantaneous velocity. So we want to find the instantaneous velocity at 6 seconds. So we can look at where that shows up on the graph, and the idea is the slope of a tangent line, or a line that just barely touches the graph at one point. The slope of that line represents the velocity if we're looking at a position versus time graph. Well, you don't have any methods to find the slope of a tangent line directly. Instead, what we talked about in our lab is if you take 2 points on equal sides of that point you're interested in. So we're interested in 6. I took 4 and 8. I could have done 2 and 10, or 5 and 7. It doesn't matter. 2 equal points, and I draw a line through that. That secant line will have the same slope as that tangent line. And I can easily calculate the slope of the secant line, so I select 2 points. Okay. So just reading those off what I drew on the graph, and I can find the slope of that rather easily. So that would be -3 meters minus -2 meters, and then 8 seconds minus 4 seconds. We do that calculation. On top we have -1, on bottom we had 4, so -1 divided by 4 is -0.25. And we see that is the correct answer here. So another follow-up question to this is, what is the acceleration of this graph? So there'll be a question like that as well. The question will be followed by a question. It will follow a question like this. So I'll ask you what is instantaneous velocity at some point, and then I'll ask you what the acceleration is. So students struggle with that quite a bit. So the idea is that we have just calculated a velocity. So if we think about that, that's a pair. That's at t equals 6 seconds, the velocity is -0.25 meters per second. And that velocity is going to change. It started out bigger, it got smaller and smaller and smaller. At 8 seconds it was 0 velocity, and then we sped up after that. So how did I know at 8 seconds it was 0 velocity? Because I can imagine drawing the tangent line at 8 seconds, and if you look, that tangent line at 8 seconds will be completely horizontal. So that gives us another time to think about. At 8 seconds, the velocity was 0. Okay, so how does this help us calculate the acceleration? Which is not shown in this problem, but like I said on the test, it will follow a problem like this. So that's where you get to basically the fundamental definition of acceleration. That acceleration is the change in velocity over the change in time. So what is the change in velocity here? Where we go from -0.25 to 0. So or you can think about it as final minus initial, so 0 minus -0.25. So our change in velocity is positive 0.25 meters per second, and our change in time, we go from 6 to 8, so that's a change in time of 2 seconds. So our acceleration for this graph would be positive 0.125 meters per second squared, and you can see how those units work out as well in the calculation. And one quick check, does your answer make sense? Well, you can see that this is a concave up parabola, and our answer for the acceleration is positive, so that's a pretty good sign. And you can see how that works out in the beginning, we are slowing down while traveling in the negative direction, and then we were speeding up while traveling in the positive direction. So those calculations of an instantaneous velocity and those an acceleration from a position versus time graph will definitely be on the test. You want to know how to do that. So we'll move on to the next problem here. This is more of a conceptual question, and I see students miss it quite a lot. In fact, it's a modification from a question I asked you on the a test I gave you at the beginning of the year. This says here's a motion diagram of A and B, and I asked which has a greater acceleration. Is it A, B, or are they both 0? Well, I think a lot of students are tempted to pick B because saying B has a greater acceleration, because you look at the spacing and the spacing's bigger. So students say, oh, it's moving faster, that must mean it has a greater acceleration. Not quite. You're confusing speed and acceleration. Speed is the amount of distance you cover in an interval of time, but acceleration is the amount of velocity you change in an interval of time. And if you look at these two pictures, both of them represent constant velocity motion. The velocity is not changing in A, and the velocity is not changing in B. How do I know that? Well, the spacing is the same. So it's covering the same distance in each interval of time. That means its velocity isn't changing. Well, if its velocity is not changing, then its acceleration is 0. The acceleration is what changes the velocity. No change, no acceleration. So once you realize that, it's obvious that the answer is C. So both of these show constant velocity motion. It's just the velocity of B is greater than the velocity of A. However, the acceleration of both is 0. Alright, so another conceptual question. This one says, rank the accelerations from each graph from most negative to most positive. Well, first of all, which are negative and which is positive? You can tell that from the concavity or the opening up or opening down of a parabola. So for one, this opens down. You know, I kind of jokingly say it's part of a frowny face. So that tells us that the acceleration is negative or less than 0. 2, the acceleration is positive because it opens up. And 3, the acceleration is positive because it opens up. So we automatically know 1 would come first in our ranking because 1 is the only one that is negative. It's most negative to most positive, so we can go ahead and eliminate these. So what about after that? Well, the next thing is we need to look at which is the bigger positive, right? Which magnitude is larger, which actual numerical acceleration is larger. So, I mean, at the end of the day, the shortcut is you look how skinny or fat the parabola is. But let's try to make sense of that, okay? So look at a point like this, and then go a little bit distance, a little bit over on the time axis, and look at another point, and compare the slopes of the tangent lines between those 2 points. In a relatively short interval of time, the slope changed quite a bit. So what does that mean in terms of the actual physics here? In a relatively short interval of time, the velocity changed quite a bit. And the faster your velocity changes, the greater your acceleration is. Again, I can't say it enough, acceleration is what changes your velocity. It's a measure of how quickly your velocity changes. We can play a similar game here on 3. Look at the 2 slopes. And again, a small interval of time. In this small interval of time, the velocity barely changes. How do I know that? Because the slope barely changes. So it is changing. That means there's an acceleration. This isn't quite a straight line, but the acceleration is very small because it's not changing very quickly. So that means this acceleration in graph 3 is small, it's positive. In graph 2, it's positive and it's much larger. So the correct ranking would be C here, because this is the only negative one, then a small positive one, then a large positive one. Okay, another question I can guarantee you will be on the test is I give you an acceleration versus, so this is kind of opposite of the first one. I give you an acceleration versus time graph, and I ask you something about the position or the path length. I'm basically asking you to go up. Okay, and this is a tricky one, but we can kind of work it out. The best thing you can do is start with a sketch of the graph above this, or what I mean is the graph of the velocity versus time. So let me just plop down two lines. That'll serve as a velocity versus time graph. So I got to go back to the annoying clicking noises to right there. Okay, and then notice it gives us some information. Our velocity starts at -1 meters per second. Okay, so I'm going to kind of sketch that there, -1 meters per second. And it's asking about the path length. Well, just let's first construct this and then worry about what the question is actually asking for. So how would I continue on this graph? Well, I have velocity versus time graph here, and what can I find out from this acceleration versus time graph I'm given? I can look at the area under this curve, which is constant because it's constant acceleration, and that will tell me the change in velocity. All right, so calculating that is just doing base times height, so I can do 0.25 times 20. I get a total change in velocity of 2.5 meters per second. So what does that mean? That means on this velocity versus time graph, if I started out at -1, 20 seconds later, all the way at the end here, my velocity has changed a total of 2.5 meters per second. If I start out at -1, at the end of that change, I'll be at positive 1.5. Okay, because of that change of 2.5. Okay, and then what would this graph look like? Well, it would be linear, because if we have a constant velocity, we have a linear acceleration. So I can go ahead and sketch that there. A straight line connecting those 2 points. Alright, so here's the difficulty. I don't know where this crosses. If I knew that, the rest of the problem would not be that difficult. There's a couple ways I can figure it out. You can set up an equation for the line and plug in when the velocity equals 0. And that's the way I'll pick to show you, but another way you can do it is you can kind of reason it out. So each one of these, every block here represents a change in velocity. How many blocks would I have to have a change in velocity of 1 to get us to 0? If you work that out, it'd be these first here, because 8 times 0.125 equals positive 1. So we're going to find out at the end our answer is 8 seconds, but I'll go ahead and show you the calculation, which kind of works out if the numbers are not so pretty. So the idea is you can set up an equation for this line. So the equation for this line is going to be the velocity equals the slope. So what's the slope? Well, that's easy. It's the acceleration. 2.5. And where am I getting this number from? From my acceleration versus time graph. And times t plus the initial velocity of -1 meters per second. And then I can plug in the condition that v equals 0, because I'm interested in finding the time that makes that true. So 0 equals all this junk. And then I can go ahead and do algebra. So I would add 1 to both sides. So 1 equals 0.125 meters per second squared times t. I apologize for the horrible handwriting. I'm doing this with the mouse. And then dividing by that we would get t equals 8 seconds. Okay, so why do we need to know that this is 8 seconds? The next thing I'm going to do here is find the area of this under the curve of this velocity versus time graph. So I'm going to find the area here. So how would I find the area here? The area here would be -1 times 8 divided by 2, the area of a triangle. So this would be -4 meters. And then I'll find the area here. This would be 12 seconds. Again, I'm thinking about the area of a triangle. 12 seconds times 1.25 divided by 2. And that would be 9. And what is this area showing you? This is showing you your displacement. So it's saying, okay, wherever you started, you walked -4 meters, so 4 meters in the negative direction, then you walked 9 meters in the positive direction. And how does that have to do with our path length? Well, our path length is just our total distance walked, so on a velocity versus time graph, the easiest way to think about that is just to think about the absolute value of these little chunks added together. So this would be 4 plus 9, or 13. So this is a very involved problem. You're not going to get it right unless you practice it, simply because there's so many steps. And try to think about what you're doing each time. What am I trying to find? Why am I trying to find it? Alright, so here's another one that's, is a little more involved. Doesn't seem like it at first, but it does require a little bit more calculation. So the idea is, here's a motion diagram. We have some information. We know the initial velocity is 2 meters per second. And I want to know what the final velocity is, what the velocity is here at the end. And you say, I don't have enough information. Well, you do. It's just a little more hidden than it is in a traditional problem where I kind of just tell you all the numbers. So what is the displacement? Well, you can read that off this graph. If we start off at -3 and we end up at 4.5, you can do final minus initial, so 4.5 minus -3. Or you can think about what do I have to add to get to here, and you would have to add 7.5 meters. So I got that off the motion diagram. You say, ooh, I still can't figure it out, yet don't have enough information. What's another thing we can get off the motion diagram is the time. Motion diagrams are implied, and I spell that out, to start at 0 seconds. So this is 1 second, 2 second, 3 second, 4 second, 5 second, 6 second. So the entire motion took 6 seconds. And now, because I have 3 givens, or 3 knowns, I can solve for any unknown. So what would you do here? It's actually going to be 2 steps, because I don't know the acceleration, and I don't know the velocity. Well, you'll notice any formula that involves the final velocity, or the velocity here at the end, requires you to also know the acceleration. There's no kind of one-stop shopping. So I'm first going to have to calculate the acceleration. I should put a VI here. Sorry, this is the initial velocity. So I'm first going to have to calculate the acceleration. And you can do that with the first kinematic equation. And it's going to be kind of annoying to write out here, but x equals 1/2 a t squared. I'm being a little sloppy with my vector hats, but hopefully you can forgive me. Okay, so with a little bit of algebra we can solve for the acceleration here. What you would do is you'd subtract vi times t from both sides, and I'll go ahead and show that. And then you would divide by 1/2 t squared to get a by itself. So I'll go ahead and show that. And I know the clicking is driving you crazy. Okay, and then now I can plug in all my numbers. I would go ahead and do that quickly in the calculator, so that'll be 7.5 minus 2 times 6 divided by 0.5 times 6 squared. Now, it's problems like these where I see a lot of calculator errors because people aren't grouping things correctly in the parentheses. So what answer do we get for the acceleration? I get negative 0.25 meters per second squared. That's not what the problem is asking for. The problem is asking for the final velocity. So it's one more step to take this acceleration and use it to solve for the final velocity. We would just use this equation here. It's the simplest. And you see how this comes together. It would be negative 0.25 times 6 plus 2. And our final velocity is 0.5 meters per second. And notice everything along the way made sense. If we were to actually go in here and draw these velocity vectors, they all point to the right. They just get smaller. So our final velocity we do expect to be positive because this is the positive direction. And we did expect our acceleration to be negative because if the velocity vectors are getting smaller, then the acceleration was pointed to the left. It was pointed in the opposite direction of the velocity vectors. Okay, so one last problem here, and we've kind of already done a version of this in 2 problems ago. But here we don't have to construct this graph from an acceleration versus time graph. We're just given the graph. And then we're asked a question about the average velocity. Well, this requires you to remember a definition that we talked about in our constant velocity unit. So the average velocity is the displacement over the time interval. Okay, so our displacement can be found from this graph by, again, finding the area of this triangle and then finding the area of this triangle. So clean that up a little bit. So the area of this triangle would be negative 1.5. I'm reading that off right here. So it goes negative 1.5 meters per second of velocity times 12 seconds. So negative 1.5, so decimal, times 12 seconds times 1/2. So I'm going to calculate that out. I'm pretty sure it's 9, but I'll double check. Okay, yep, negative 9. So this displacement here is negative 9 meters. What about this guy here? This would be 8 times 1 divided by 2, so that would be 4. So we can take these two little chunks of displacement, so negative 9 plus 4. So our total displacement is negative 5 meters. Our path length here would again be negative 5, or sorry, our path length would be 13 meters, because for path length you would ignore the direction. But for displacement it's negative 5, and then we divide that by the time interval of 20. Well, negative 5 meters divided by 20 seconds is negative 0.25 meters. So again, what is average velocity? It's saying you spend some time moving in this direction at this speed. That speed's always changing, and the direction changes. Take all those different velocities, and if you can imagine the average for the trip, that's how you would calculate it, taking the displacement divided by the time. Okay, so that's all the problems I'm going to do in this video. Feel free to email me if you have other problems. I apologize for the length, and I apologize for the clicking.